Exercise 1020 is meant to help you predict the products of the hydroboration-oxidation reaction on alkynes. Now, hydroboration-oxidation is a reaction that we've seen already with alkenes. It adds H and OH across a double bond, across one pi bond, in an anti-Markovnikov way. Now, when that happens to an alkyne, you end up at first, you have the same number of carbons, you use one of the pi bonds to stick an H on there, and then you have the OH, but the other pi bond is still there. And notice I've added the H on the more substituted position because this is anti-Markovnikov addition. So what we saw in the sort of previous chapter was that when you do hydroboration-oxidation, so some sort of boron molecule, in the previous chapter it was BH3 stabilized by tetrahydrofuran. In this chapter it's a little bit different, we'll talk about that in a second. But it's some sort of boron compound followed by hydrogen peroxide and sodium hydroxide. You add H and OH in an anti-Markovnikov way, and you lose one pi bond. So that's what's happening here. And I have an animation for the mechanism for that, which is kind of long and complicated in the playlist for the alkene reactions for the previous chapter. So if you're interested in that, I encourage you to go there to see how that's happening. Once you have this, notice that you have an enol, an alkene with an alcohol attached to it, an OH on it. And so that enol tautomerizes, just as we've seen in the previous videos in this chapter. And so the double bond ends up going to the oxygen, and the hydrogen moves over. Now notice this has a hydrogen here, and this is a different functional group. It's not a ketone, it's an aldehyde. An aldehyde is when you have a carbon double bonded to oxygen with a hydrogen on at least one side. The smallest aldehyde is one that you have probably heard of. If you have a carbon double bonded to oxygen with a hydrogen on both sides, that is formaldehyde. Formaldehyde, that's the smallest aldehyde. But aldehydes in general are any molecules that have a carbon double bonded to oxygen with a hydrogen on one side. And so when you do this hydroboration-oxidation on a terminal alkyne, a triple bond that's at the end of a carbon chain, you end up getting these aldehydes. Okay, now one note about how this recipe is different. So the mechanisms for these we've done in previous videos, and if you want to see those, I encourage you to watch those. For this exercise, we're going to focus on just predicting what the aldehyde looks like for different alkynes that you start with. But before we do that, I just want to mention one thing about how this recipe changes just a tiny, tiny bit for alkynes as opposed to alkenes. With alkenes in the previous chapter, the boron could have 3 hydrogens. It really didn't matter how many hydrogens the boron had, because you're starting with a molecule that only had one pi bond and so could only react once. But here we have 2 pi bonds, and so this could technically react twice with this molecule. But to get the product that we want, we only want it to react once. And so we replace 2 of those hydrogens with things that won't react. With carbon chains. Now, 9-BBN is a bicyclic compound looks a little bit like this. So it's bicyclic, you have the boron attached to carbons on 2 ends, and you have this one hydrogen there. So that's 9-BBN. So that is also an example of this Br2H. Remember, capital R just means any carbon chain in organic chemistry. So a specific example of R2BH is 9-BBN. And it's really nice because these boron compounds tend to be toxic. 9-BBN is a solid. And if you're ever going to deal with something that's toxic, it's always better to deal with a solid than a liquid, and that's even better than a gas, because a solid is the easiest to contain, and the next easiest are liquids, but liquids evaporate and gases are really hard to contain. So you're almost guaranteed to breathe in some of it unless you're extremely careful. So that's our recipe, that's our plan. Let's apply that to some specific molecules. Now, they give you the alkyne, and they give you the recipe for hydroboration-oxidation. So the first step is just to redraw the molecule, but with all single bonds between the carbons. So notice here, if it helps number the carbons, we have 1, 2, 3 of them on this cyclohexane ring. So 1, 2, 3, and there they are. Now, of the 2 carbons in the double bond, this is anti-Markovnikov addition, so the oxygen is going to go on the less substituted one. This one on the end is primary, and the one in the middle is secondary. Right? This one is bonded to just 1 carbon. This one is bonded to 2 carbons. So because this is anti-Markovnikov, the double bond to the oxygen after the keto-enol tautomerism is going to go on the primary carbon, the less substituted one. And just write in that hydrogen there. It's good practice when you're drawing aldehydes to write in the hydrogen, because it's part of the functional group. And so that's it. That's the product you'd expect to get when you do hydroboration oxidation. First 9 bbn, then second as a second separate step. And don't forget to include these steps, because if you mix all this stuff together in one flask, it'll react with each other and not with the carbon chain. So first 9 bbn, second separately H2O2 and NaOH, hydrogen peroxide and sodium hydroxide, and you end up with this aldehyde. Okay, let's try the same thing here. This dicyamylborane may not look familiar, but it's really just one of these R2BHs. And hopefully, certainly on my test, there won't be any random ones that come up. The only possible things I'd put on there would be something where you can clearly see you have 2 R groups, or something that's in the homework, so 9 bbn or dicyamylborane. Dicyamylborane is sort of like has 2 isobutyl groups on each side, but the first carbon also has a methyl group. So that's a cyamyl group. It's not something you necessarily need to know, but there's 2 cyamyl groups, 1, 2, so that's dicyamyl. And then you have the 1 hydrogen here. So notice how this is an R group here, this is another R group there. Those are your 2 R groups. And then you have the BH. Okay, so this is really a recipe, and then the second step, hydrogen peroxide and sodium hydroxide. So this is really a recipe for hydroboration oxidation. And what we're given is an alkyne. So the first thing to do is to redraw the alkyne, but with all single bonds. So let's say we have 1, 2, 3, 4 carbons as a sort of backbone. 1, 2, 3, 4. And on carbon number 3, we're going to have 2 methyl groups. So 1, 2. And then just in here, if it helps, 1, 2, 3, 4. So you could see on carbon number 3, we added the 2 methyl groups. Now, this is anti-Markovnikov addition. So the double bond to the oxygen is going to go on the less substituted carbon. Notice that the one on the left there is primary, and this one is secondary. So the double bond to the oxygen is going to go on the less substituted position, the primary one. And just draw that hydrogen in to remind people that what you have is an aldehyde. And so that's the aldehyde that you would have if you did this hydroboration oxidation on this alkyne. Okay, so here we have this big ring again, and if you number it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so the first step is to just redraw this, but with all single bonds. You can sort of copy the top except for the bottom part of it. So just copy the shape of that molecule there. And then these are going to be our 2 carbons here. So there. So if you're numbering that, this would be 1 and 2. And then you'd go around 3, 4, 5, 6, 7, 8, 9, 10, 11. So those are our 11 carbons. And we know that the we're going to draw a double bond to an oxygen, and it's going to be on the less substituted carbon. That's what you do when you have hydroboration-oxidation of an alkyne. But here, both of the carbons, and we know the carbons that are going to react are the ones in the with the triple bond on it, but both of those are equally substituted. This one is secondary, and this one is also secondary. They're both bonded to 2 carbons. Which means that you'll get the double bond to the oxygen on both of them. And the truth is the molecule is symmetrical, so either one you put it on amounts to the same thing. But if you want to just cover your bases, you can put it on carbon number 1 or on carbon number 2. Either way. Either way, those molecules are the same. They have the same number of carbons going around on each side. But those are the possible products that you get here. Now notice we didn't technically get an aldehyde on this one, but that's because we didn't have a terminal alkyne. So you'll get an aldehyde if you have a terminal alkyne. If you have an internal alkyne, then you'll end up getting this ketone. So that's an interesting thing to note. Okay, so hopefully that gives you some practice with just predicting the products, drawing the products of a hydroboration-oxidation of an alkyne. You'll put a double bond to an oxygen, redraw the molecule with all single bonds, and put a double bond to an oxygen on the less substituted carbon. And if the carbons are equally substituted, you'll get a mixture of the double bond to the oxygen on each one, on each carbon that was in the triple bond.